Welcome back to the Talking Ketamine podcast. This is episode 59, Ketamine, the Cognitive Enhancer.
It's great to be here. Today we are looking at a 2026 review by Leon-Rojas and Sacks-Zimmerman. We usually think of ketamine as something that makes you space out or forget. But this paper asks a radical question. Could it actually be used to make the brain sharper and repair cognitive decline?
Oh, wait, isn't this famous for making people space out, disconnect, or forget things? Like, how on earth can a drug that causes temporary cognitive impairment become a candidate for cognitive enhancement?
Right. I mean, it is a massive paradox.
Right, it sounds completely backwards.
Your skepticism is entirely justified here. I mean, historically, medicine has been super focused almost exclusively on the acute, immediate effects of this substance.
Which makes sense because right after you take it, you wouldn't exactly sit down and take a math test.
Exactly, you wouldn't. Your reaction time slows down and your working memory just kind of goes offline temporarily.
Yeah, which is why it's a staple in operating rooms, right? Like it just shuts things down.
Right. But what this 2026 systematic review forces us to do is look past that short window of intoxication. We are actually witnessing a massive paradigm shift in neuropharmacology.
Okay, a paradigm shift how?
Well, the scientific community is moving from viewing this merely as a way to numb pain or treat severe depression to investigating its potential as a true neuroprotective agent.
Wait, a neuroprotective agent? So it's protecting the brain long after the drug is actually gone?
Yes, exactly. We're talking about a substance that appears to fundamentally alter and, repair the microscopic architecture of the brain in the days and weeks after it clears your system.
Oh, wow. Okay, so the temporary impairment is almost like putting up scaffolding and closing down a street so a construction crew can get to work.
That's a great analogy. Yeah.
Like,
Good.
it's not about what happens while the street is closed. It's about the newly paved road that's left behind after the crew goes home.
I mean, that is a much better way to frame it. We've been so hyper-focused on the temporary street closure, like the immediate numbing or the psychological trip, that we've completely overlooked the structural remodeling happening behind the scenes.
Right. So let's talk about why that remodeling is necessary in the first place. For you, the listener, if you or a loved one are facing these conditions, what does the biological wreckage actually look like?
Well, the researchers cast a really wide net across several heavily destructive diseases. They pulled data on traumatic brain injury or TBI, cerebrovascular disease, which most of us just know as stroke, Parkinson's disease.
Wait, Parkinson's too.
Yeah, Parkinson's, epilepsy, and even infectious encephalopathy.
I mean, that's a bizarrely diverse list. A blunt force TBI seems mechanically entirely different from a slow, progressive condition like Parkinson's.
On a macro level, looking at a brain scan, sure, they look very different. But at the microscopic cellular level, they actually share incredibly destructive common pathways.
Okay, so what's the common denominator there?
Whether the initial trigger is a physical impact, a blocked blood vessel, or a genetic misfire, these conditions all generate toxic, chronic levels of neuroinflammation.
Oh, wow.
And that severe inflammation leads to a massive, accelerated die-off of synapses.
And since synapses are the physical bridges where electrical and chemical information crosses between brain cells, their destruction is what actually translates to the symptoms we see.
Exactly. When those microscopic bridges collapse in large numbers, the macro effect is cognitive decline. The signaling network literally falls apart.
So it's kind of like if we imagine the healthy brain as this vibrant, fully illuminated city, a condition like a severe stroke is like a slow-moving hurricane tearing through the infrastructure.
I love that, yeah. The physical trauma rips down the power lines.
Right. And as the storm continues, the broken lines cause massive secondary damage, and different neighborhoods just start to go dark. Like, one grid failing might mean losing your short-term memory, and another going dark means losing your spatial awareness.
Right. And the major issue with traditional neurology is that our treatments for these dark neighborhoods have mostly been compensatory.
Meaning, don't fix the grid?
No, we don't have many tools to rebuild the power lines. We usually just give the patient a flashlight and try to teach them how to navigate their house in the dark through behavioral adaptation.
Right, which perfectly defines the stakes of this review. If this drug actually steps onto that battlefield and rebuilds the power lines, how on earth does it do it?
It comes down to a very specific two-phase biological mechanism. Let's start with phase one. We can call it the fire extinguisher.
The fire extinguisher. Okay, break that down for us.
So sticking with your city hurricane analogy, when a brain is damaged, say, right after a severe impact in a TBI, the dying brain cells rupture and spill their contents.
Okay.
One of those contents is a chemical called glutamate.
Which is normally a good thing, right? Like the spark that helps signals travel.
In a healthy brain, yes, it's a vital excitatory neurotransmitter. But in an injured brain, you get a massive unregulated flood of it.
Oh, wow. So too much of a good thing just becomes a lethal toxin.
Exactly. It becomes a biological chemical fire. This phenomenon is actually called excitotoxicity.
Excitotoxicity.
Yeah. The excess glutamate floods the surviving healthy cells by forcing open specific cellular doorways called NMDA receptors. It overstimulates them until they literally burn out and trigger their own death.
So the secondary damage is often worse than the initial injury itself.
Often, yes. And this is where the medicine comes in. Ketamine is fundamentally an NMDA receptor antagonist.
Meaning its chemical shape allows it to physically plug those cellular doorways.
Right. It blocks the receptors, stopping the toxic flood of glutamate from entering the healthy cells. It acts as a chemical fire extinguisher, immediately shutting down the excitotoxicity.
Okay, I understand stopping the act of destruction.
Right.
But like, putting out a fire doesn't rebuild a burned down house. It just leaves you with wet, charred wood.
Right.
So how do we actually get the neighborhood's power grid back online?
That brings us to phase 2, the fertilizer.
The fertilizer.
Yeah, blocking those NMDA receptors and putting out the fire forces the brain to compensate. It triggers a profound downstream cascade, rapidly releasing a surge of a protein called BDNF.
Brain-derived neurotrophic factor.
You got it. BDNF is essentially biological miracle-grow for the nervous system. When it floods the cortex, it signals the neurons to start branching out.
Oh, wait, like physically branching out?
Yes, it promotes a process called synaptogenesis. The brain literally begins to sprout new dendritic spines, tiny structural arms that reach out and form entirely new, healthy synaptic connections to bypass the areas destroyed by the trauma.
So the hurricane knocks down the city's power grid, creating live sparking wires. The medicine acts as a fire extinguisher to stop the sparks from burning down the remaining houses, and then it simultaneously releases this fertilizer to rapidly grow new, organic wires around the wreckage.
That is the mechanical promise observed at the cellular level, yeah.
But, I mean, mechanistically promising doesn't always mean practically useful. How does growing new, microscopic arms on a neuron translate into a patient actually remembering their grandchild's name or successfully navigating their kitchen?
That's the real gap we have to cross, and it's exactly why the researchers compiled this data. They wanted to know if this cellular theory holds up when you subject a living organism to rigorous cognitive testing.
Right, so let's look at the actual evidence from the 22 studies analyzed in this 2026 review, and we need to point out right away that there is a massive translational gap here.
Yes, there is.
Because out of those 22 studies, 21 of them were conducted on animals.
Yeah, the vast majority of the data comes from 366 rodents. These were rats and mice that had been scientifically induced with models of TBI, epilepsy, stroke, and Parkinson's.
The results the paper cites for these animals are staggering, though. They report an overwhelming 93.2% success rate in observing positive cognitive effects.
It's an incredible number.
But wait, how do you even test working memory or spatial learning in a rat? It's not like you can ask them to recite a phone number. How do we know their cognition actually improved?
It's a great question, and the methods are actually quite sophisticated. Researchers use behavioral assays, like the Morris water maze.
What's that?
They place a rat in a small pool of opaque water with a hidden platform just below the surface. The rat naturally swims around until it bumps into the platform and climbs up.
All right.
Over a few days, a healthy rat uses visual cues around the room to memorize exactly where the platform is and swims straight to it. That requires intact spatial learning and working memory.
So a brain-damaged rat from the control group would just struggle to learn the location.
Exactly. The control rats with mottled brain injuries will often swim aimlessly day after day, unable to form the memory map of where the safe platform is located.
And the treated rats.
The rodents that received the treatment post-injury behaved almost like healthy rats. They were able to navigate the mazes, recognize novel objects in their cages, and recover their functional memory far faster than the untreated group.
Wow. So that 93% success rate is based on these highly measurable functional outcomes.
Right.
But 93% success in rebuilding memory pathways after a brain injury sounds like a miracle. But anyone who follows medical research knows that we have cured Alzheimer's, cancer, and stroke 1,000 times over in mice.
Oh, absolutely.
Drugs that work perfectly in a rodent's brain often fail completely when introduced to the vastly more complex human cortex. So what happened in the single human study included in this review?
This is the critical reality check of the paper. There was only one human trial that met the strict criteria for this systematic review. It involved 10 human patients suffering from Huntington's disease.
On the results.
They were definitively negative. The study documented a dose-dependent negative influence on cognition.
Wait, really?
Yeah. The patients experienced significant impairments in immediate verbal recall, a noticeable decline in their verbal fluency, and slowed physical and mental reaction times.
I mean, if you are listening right now and hoping for a breakthrough, that has to sound incredibly disheartening. We just spent all this time outlining an elegant biological mechanism of fire extinguishers and brain fertilizer, and the single time they tested it on humans in this review, the patient's memory and speech actually got worse.
It looks like a massive contradiction on the surface, but we have to look really closely at how and when these humans were tested, as well as what disease they had.
Okay, break that down.
The human subjects were given escalating intravenous infusions, and their cognition was tested a mere 2 days after the exposure.
2 days. So they were essentially still in the shadow of the acute intoxication phase we talked about at the very beginning of the show.
Exactly. They were taking complex cognitive tests while their nervous systems were still recovering from the immediate impairing effects of the drug.
They tested the patients while the street was still closed and the scaffolding was still up.
Precisely. Furthermore, Huntington's disease is a severe, genetic, progressive neurodegenerative disorder. It is an entirely different beast than a single acute event like a traumatic brain injury or a stroke.
Because with a stroke, the hurricane passes and you can rebuild. With a genetic disease like Huntington's, the hurricane is constantly regenerating itself. You are trying to rebuild a house that is actively on fire from a genetic level.
That is a crucial distinction. The fertilizer can't outpace a fire that never stops. But even beyond the specific disease, the testing timeline of 2 days highlights the most vital concept in this entire field of research.
Which is?
The golden rule of this potential treatment is that dose and timing dictate everything. We have to completely separate the short-term side effects from the long-term structural repairs.
So we're talking about the difference between an anesthetic dose and a subanesthetic dose.
You cannot overstate the importance of that difference. If you administer a heavy anesthetic dose, you are quite literally shutting the brain's higher functions down for surgery. It is a suppressive event.
Right.
But if you administer a subanesthetic, low dose, the pharmacological profile changes entirely. It acts as a signaling mechanism. It's a biological tune-up that triggers the BDNF release without putting the system into a coma.
So more is absolutely not better here.
More is actually detrimental to the goal of cognitive enhancement. The low dose is what opens up the window of neuroplasticity.
Let's really drill down into that phrase, the window of neuroplasticity.
Yeah.
Because I think this is where the public perception of cognitive enhancers gets things totally wrong. The goal isn't to take the medicine, sit in a clinic chair, and magically be able to solve a complex puzzle or recall a lost memory while the IV is in your arm.
No, the medicine itself contains no information. It is not injecting new knowledge or raw intelligence into your cortex. What it is doing is warming up the biological clay. It is returning a rigid, damaged brain to a highly malleable state. The true medical magic happens when you use this pharmacological tool to open that window, and then you rigorously apply traditional neurorehabilitation.
Let's put this in a real-world clinical context.
No.
If someone survives a severe stroke, they're usually prescribed physical therapy, speech therapy, and occupational exercises, right?
Correct.
But so often, those patients hit a frustrating plateau. They put in hours of work, but the damaged brain is too rigid to adapt, so their progress just stalls.
The limitation isn't the patient's willpower. It's the lack of biological resources to build new pathways. But imagine if you administer a subanesthetic dose of this medicine to that stroke survivor.
Okay.
You clear out the toxic inflammation, release the BDNF, and open a window of neuroplasticity that lasts for several days or even weeks. During that specific window, you have them perform their intensive speech and physical therapy.
Because the brain is now primed and flooded with fertilizer, it actually builds the new synapses exactly where the therapy is demanding them. It's use-dependent plasticity.
That's the key. The therapy dictates where the new connections go. The medicine simply provides the materials to build them. This perfectly explains the gap between the rodent success and the human failure in the review.
Because the rodents were subjected to spatial learning tasks, like swimming in mazes and exploring new objects over an extended period of time, they were actively doing cognitive rehab while their neuroplasticity window was wide open.
Exactly. While the human study simply administered the drug to patients with a progressive genetic disease and tested their baseline recall 2 days later without any integrated ongoing cognitive training.
They expected a magic smart pill, and what they got was the residual hangover of an anesthetic.
The authors of the review are quite blunt about this. They emphasize that future human trials must fundamentally redesign their approach. We cannot just measure acute recall at 48 hours. We need to measure the long-term durability of cognitive gains weeks and months after the treatment, and it must be done in conjunction with active, targeted cognitive remediation therapies.
It's fascinating to think about how the cultural and historical framing of a medical tool can delay our understanding of its true potential. Because of its reputation as a dissociative anesthetic, we've spent decades viewing the temporary cognitive blunting as an unfortunate side effect we just have to tolerate.
Or a reason to avoid the drug altogether in vulnerable patients.
Exactly. But by stepping back, we are realizing that the blunting is just the messy construction zone before the new architecture is unveiled.
It really challenges a deep-seated dogma in neurology. For the longest time, the medical consensus was that the adult brain was relatively fixed. Once brain cells die from trauma or a stroke, that's it.
Right. The power lines are down forever, and the best we can do is teach you to walk around the debris.
Exactly. You just have to learn to live in the dark. But if we can reliably, pharmacologically open a window to spark synaptogenesis and rewire around those devastated areas, it upends the idea that adult brain damage is a permanent static state.
It turns out the brain is far more resilient and capable of structural regeneration than we ever gave it credit for.
It really is.
It makes you wonder if we can artificially open up this window of neuroplasticity in damaged brains to rebuild lost connections. What happens if we eventually figure out how to safely open it in healthy ones?
Exactly. And that forces us to look at this in a completely different way.
So the very medicine that temporarily disconnects us during a treatment might actually be the key to physically reconnecting the brain's fading memories and skills.
Exactly. We are moving from using ketamine just to numb pain or lift sadness to actually using it to protect and rebuild the architecture of the mind itself.
A whole new frontier for neurology.
Thanks for listening to the Talking Ketamine podcast. We'll catch you on the next one.